Okay, so we would expect if light were behaved as just a classic wave, that the and whose intensity of a light wave would basically be proportional to the square of the amplitude of the electric field. We'd expect that if we cranked up the electric field, so we crank up the intensity, that wave would carry more energy. Okay, and just like a water wave, a larger water wave with larger amplitude carries more energy, we would expect that there would be more electric current, more photoelectric current generated by when the intensity is cranked up. The other thing that we should maybe expect is that if we think about an atom, okay, where we have some positively charged nucleus, and then we have electrons which are going around in some orbit, okay, that some sort that we know that this electron is bound to the nucleus, okay, and so a material which is composed of lots of atoms, okay, we know that the electrons don't just go flying out of the material willy-nilly, because otherwise all materials would end up positively charged after some time. So we know that the electrons are bound somehow to the nuclei within the material. Even though there's not just one atom, there's still sort of a binding energy. And so it would take some amount of energy in order to overcome this binding, and in order to liberate the charges, now we know they're electrons, to make this current. Okay, and so in the context again of light as a wave, we would expect that there would be some threshold intensity, some threshold electric field amplitude that would result in a that would result in any current at all. And if we had less than that intensity, we wouldn't get any photoelectric current. Okay, and furthermore, that since the dependence on the frequency of the wave, okay, which is again inversely related to the wavelength, it drops out of this sort of picture, because the intensity, when you square the electric field to get an intensity, then the frequency dependence drops out. That this minimum threshold intensity that would generate a photoelectric current would not depend on the frequency. Okay, so that's basically what you would expect if light were purely a wave, in terms of how this current through the circuit would depend on the electric field, on the intensity. Okay, now let's see. Back in the late 1900s, there were people started to study this photoelectric effect, and they started to notice some interesting things that were hard to explain within the context of what they knew at the time. So, for example, Heinrich Hertz, in 1887, a German, he was basically just studying electromagnetic waves. So the term Hertz, which is a frequency unit, right? It's a inverse second, was named after Heinrich Hertz, and he was studying electromagnetic waves, and he basically just wanted a way to make electromagnetic waves, a way to make light, and then he was studying various properties, and he was using a spark gap, basically two sharp points that he connected to a battery, something like a battery. So we know, right, if we take our jumper cables and we connect them to our car battery and we get them very close, if we touch them, we'll get sparks. Okay, and so he was just using these sparks to sort of a spark creates a burst of light, and so he was using that to create light to study electromagnetic waves. And one of the things that he noticed was that if he shielded his 2 points from light, that is, if he shielded the spark gap from external light, then he had to basically put the 2 points closer together. He had to reduce the distance between the 2 points. He had to reduce the gap in order to generate a spark for a particular voltage that he applied between the two. Okay, so this basically makes sense in terms of the discussion we've already had, because if you have light shining on this system, then that can generate electrons which can short circuit the spark. We can short circuit the spark, and that all makes sense.